Good morning, guys. Good
Hi,
morning, Dr.
everyone.
Gordon.
Hi, Dr. Mehta.
Good morning.
Morning, Professor. Good morning, Dr. Gordon.
Good morning.
Do you want to get started, Imdadul?
Yes, we can get, is everyone here?
Yeah, he just joined. Imdadul has just joined.
Okay, great.
Imdadul, you can start the
Good morning, Dr. Gordon.
Morning.
Please make sure that you can see my screen.
Here we are, yes.
Good morning, everyone. In continuation with our previous presentation, today I'm going to present our literature review on challenges of unmodified and modified hot mix asphalt binders and mixtures and a roadmap to potential sustainable solutions. In our last presentation, it has been discussed that the properties and performance evaluation of nanomodified asphalt binders and mixtures has to be identified, and also the challenges we have that associated with these nanomodified asphalt binders, and also the effect of different additives and also these nanoparticles on the environment and human health, and also the need for the life cycle cost analysis of these additives. So in our today's presentation, four studies will be presented, where first we will start with the types of different nanomaterials which are being used in the asphalt industries and their properties, benefits, mixing methods, performance evaluation, and also to resolve one of the issues that we have with this nanomodified asphalt binders, which is storage stability, it will be also discussed, and the environmental impact of these nanomodified asphalt binders, and the life cycle cost analysis of nanosilica modified asphalt mixtures. So to start with the nanomaterials in asphalt mixtures, we can directly go into the types of nanomaterials which are being used in asphalt industry till now. So in this study, more than 150 studies have been summarized, and it has been found that 25 types of nanomaterials are being used in asphalt industry still now. So from this pie chart, can you see my pointer?
Yes.
Okay. So from this pie chart, we can see the nanosilica, nanoalumina, nanoclay, nanotitanium, nanozinc oxide. These are the most used nanoparticles in asphalt industry till now. And we can also see some pictures from like nanosilica, nanoclay, graphene nanoplatelets, nanographene oxide, and different like carbon nanotubes, different nanoparticles. In these studies, the types, the properties, and the mixing method of different nanomaterials has been studied, and their dispersion, also their rheological properties for the of these nanomodified asphalt mixtures has been identified, and eventually they also summarize the performance of using these nanoparticles in asphalt industries to identify the different like performance parameters, the improved rotting resistance, fatigue cracking, moisture damage, and etc.
A comment on this is that you see how you have this is you mentioned 25 different materials, right? And then you see that the 22%, the 17, the 12, and then maybe the 6 and then the 4, right? The 4s would rank, it would allow you to rank the top, let's say 5, 6, 8, right? Whatever those are, right? So that someone looking at this could easily pick out, all right, what are the majors, right? And instead of me now looking at 22% trying to find the brown in the mixture, right? I mean, have this what you did, but also list out the top 8, the top 10. I mean, even if it was double, right, with the 4 and 4, you'll have the doubling. But at least I can now look at, okay, what are the top 8, right? Maybe 8 is good because then it goes down to 1, right? I think a lot of the 4s are in there, but I can't tell the colors, right? Because they're small dots, and then I gotta look around and my eyes are going everywhere. So and then my next question would be, why were these the leading ones? Were it random? Were the particular properties that followed through? Was it was it governed by I guess reflective properties, other properties that are needed, and then the citations around it, right? That would give you, if nanomaterials were the thing I was going to expand on, I would want that, right? But before I forget to do this, right? I replied you guys on the WhatsApp, but I wanted to highlight to you, if climate extremes and EV impact were going to be something I wanted to get my attention, right? To get the attention of the readership, then I might change my title to things like, I'll just give you examples: urgent innovations, right? So throw in the word urgency, for sustainable pavement, addressing climate extremes and EV revolution through modified hot mix asphalt, if that's your thing. And then there are other alternative titles that are more clever. This may be paving the way, and then urgent solutions for climate resilient and EV ready hot mix asphalt, right? That, and modifying the title of what you wrote me, right? Another one is hot mix asphalt under pressure, right? So yeah, so innovations for roads amidst climate and EV challenges, right? And then another one, driving change, right? Because people drive, so you use the word driving change, adapting asphalt for extreme climate and electric vehicle revolution, right? So extreme climate allows you to not talk about UV yet, but inside the writing to do that, right? So think about that, right? And then another one is roads at the crossroads, right? Climate challenges, EV traffic, or you spell it out, electric vehicle traffic, and the future of past hot mix asphalt, and then people start thinking about how they modify, and then another one would be critical distress, tackling climate extremes and electric vehicle demands with modern asphalt solutions, right? So that then you now have, right, instead of saying we're smarter, right? I don't like that, because it was what they had was good for the time that it served, right? But then going forward, right, we need to consider these things. And has the research, without our review paper, right, without this publication, if you read this, it may help you, every researcher out there, to tweak your mindset, right? Then everybody wants to tweak their mindset, and then they read our publication, and then they reference it in all of their publications, right? And then now your citation score skyrockets, right? So that I'm just wanted to give you, just even in the title. Now in the outline, what you would then do is you would then intersperse these things into like, let's say, components of the hot mix asphalt pavement. You would have binder of the aggregate to mixtures with attention to modern demands, right? And then you'd classify the rising temperatures, extreme weather events, and their consequences, right? Under effective climate extremes on hot mix asphalt. So that might be section, I think, instead of two, right? I looked at it and said, okay, but maybe 2.2 is that. 2.3, impact of electric vehicle traffic on pavements, increased load and thermal stresses from EV batteries. So that might be, helps you contextualize this. So I don't want to write this for you, the outline, but I wanted to show you if I were to intersperse this stuff in there, right? Then what would be one of the things I do? So I'm going to in the WhatsApp while you present, I will put these and again, even though I abbreviated to be quick, don't abbreviate. And then the titles, they're in the recording that I just mentioned, but you just listen to the recording, and then you'll have some of these titles, all right? But I just put in WhatsApp an expansion of 2 to interweave, right? The urgency. Hope that helps you.
Okay, understood. Yeah,
Okay.
that helps actually.
Okay. I'll keep going.
Okay, thank you. So the properties of these nanomaterials have been summarized in this paper. We can see their nanometer, surface volume ratio, density, melting point, color, and appearance for different nanomaterials here. And the different mixing method has been identified for this nanomaterials, while high shear mixing method, mixing with ultrasonication, composite mixing method has been identified. We can see the equipment which are used in high shear mixing, and scanning electron microscopy and FTIR has been used to to identify the different chemical compositions with these nano particles. We can see the ACM images of different nano-modified asphalt here, starting with the nanosilica, nanohydrated lime, nano zinc oxide, and so on. And the interaction between these nano particles with the asphalt binder has been identified in this paper as well, where we can see while using the organocell, after the hydrolysis of organocell, the methyl hydroxyl group has been replaced with the hydroxyl group, and then after addition of nano zinc oxide, the silane nano zinc oxide composite has been produced eventually, which added to asphalt binder due to its polarity later, and this chemical bond of nano-modified asphalt reduced the damage properties by reflecting and absorbing the ultraviolet radiation due to the delay in the formation of sulfoxide group. And these are the physical properties of nano-modified asphalt, where we can the CA is for the control asphalt and NMA for the nano-modified asphalt. We can see for some of the nanomaterials, suppose the nanoclay and also the nano titanium oxide, nano zinc oxide, they improves the ductility of the nano-modified asphalt. And
Can you go back to that chart? I want to look at the numbers a little longer. Okay, so
yeah.
The ductility, okay, and then what is the temperature? That's the temperature that it can go down to, that it has still ductile, or what does that mean?
For these temperatures, this ductility test has been done. I mean, for different nanoparticles, because they summarize different papers here in this their literature review. So,
okay, so let's use nano zinc oxide, right? So at 5%, you've got you can penetrate to 0.1 millimeters at 25 degrees. Is that right? If I'm looking at penetration?
Yeah, that's the penetration.
Okay, and then you can achieve ductility. Is that you can achieve ductility at 5? What go to the ductility column? What does that mean? 5 and 10, because they're both at the same percentage. Nano zinc oxide, right?
So, Dr. Gordon, let's say actually for zinc oxide, so at the temperature of 5 degrees centigrade, for the control asphalt, the ductility is 6.8, but for the nano-modified asphalt, the ductility value is 7.8.
Okay.
Yeah. So
Okay, so they're
there is
saying,
an improvement in the ductility value with the addition of
Okay.
nanomaterial.
Okay, so there's improvements, but normally if you did nothing, it was at the control was at 5. Is that what they're saying?
Yes. If we don't add this nanomaterial, like the control binder has a ductility of 6.8 at 5 degrees Celsius.
Okay, so okay, so the
These are
CA,
the temperatures.
the CA column is the control.
Yeah, this is the control,
Correct.
and this is nano-modified asphalt.
Okay, can you just you know, in the future adjust that out, because it's hard to know what CA is, right? Just write control asphalt, and then or get, you know, since we all know it's asphalt, then just control and then nano modified, so that it's nice and clear. Right? Otherwise, if I miss this, then I might not be able to follow. So in the second row, right, of the nano zinc oxide, why did the nano modified go down from 18 to 10? Why did the ductility go down? Because the
Yeah,
temperature is now higher, therefore it's not, it affects it. It has to be, it's only ductile, more ductile at 5.
yeah. So they summarized different studies here. So
Right.
that study was conducted in 5 degrees Celsius, but the other one they found it was in 10 degrees Celsius. So
Right.
so in that paper they found that with the increasing in temperature, the ductility actually reduces, while at 5 degrees Celsius it gets the better ductility.
Yeah. And then, you know, numbers are, it's always good to look at percentages, right? So generally speaking, all right, so we are going in the wrong direction of the ductility according to the papers as you tested at 10 degrees, right? And that is the addition of the material at 10, or, you know, after you've added it, now when at a higher temperature, it's not a major improvement at a lower temperature, but at double the temperature, and most things are not at 5 and 10, right? You know, unless it's a freezing day. So what is it at room temperature? So then I look at, you know, they don't have that. I mean, do they have that, and you didn't put it in there, or they didn't do it at all?
No, they didn't do, because they
Mhm.
summarized the results from different studies.
Uh-huh.
They didn't conducted this test by themselves. Suppose
Right.
for the graphene oxide, the test was conducted in room temperature. So they presented the value for room temperature for graphene oxide. And also
So is increasing ductility that's a good thing, right? We want that, right? Or no? We don't want it, or we want it?
We want it. Yeah.
Right, we want it, right? So
Right.
if we want it, right, another way in your presentation, right, in the future is, you know, you highlight the ones we want, right? And then you make it green. So right, so let's say the top one was green, and then the many of them, or they're only moderately green, right? And then most of them are not green. So it doesn't give you the property that you want in this classification. But also in this paper, remember, we want people to read it and say, oh my goodness, thank you guys for coming up with this, because it not only changed my thinking, it allows me to see how while research was done, it wasn't done with the mindset of urgency, right? It wasn't done with the mindset of the climate extreme, let's say UV in this, you know, example, or from a perspective of reusing the material, let's say, right? So I'm going to give you an example of fluorinated compounds, excellent properties in water repelling, and it's somewhat fatty and things like that. But if it's a forever chemical, right, under that classification, then now we can't use the material as it breaks down, because everything will break down. You hope it will break down to something that we can use. So what elements are important, right? So when titanium would probably be the lesser, right, compared to zinc, which is prevalent, calcium, which is on the surface, right? the things to think about like that, right? So it's a matter of perspective when we write these things, right? And so we also want to expedite the if you're presenting and someone's looking at this very quickly, you want to showcase that the percentage improvement and also which direction, right? Well, obviously, I mean, I would think of the ductility being helpful, right? So highlighting that very quickly, so I don't have to do the calculation between nano zinc oxide and let's say nano titanium oxide, but it is obvious that you have a 1 point increase and then the other one is only 0.4 increase, right? Or 0.3 increase, right? Nano titanium dioxide. So zinc oxide is better on the ductility level, right? Yeah.
Understood.
Yeah. Anyway, just making it so that we're not just if we were in Yellowstone, right, a national park, some people drive right through it and say, "Oh, I've seen everything," right? Or they go on a tour and they've seen it, and others will spend time at one location for a day to see what's there, and then they'll even go back to the same location because different animals will come out, other things will come out. So you may be different. You may have had a different people around you, others, your perspective changes as your environment changes, right? So as you slow or you alter your presentation, right? Then the brain just responds very differently, right? And I need to present what you're presenting to me into a very positive. They're going to ask me, what did you do with the grant money, and what did you do all these months, right? So I need to I will present, you know, it's not so easy to get everybody into the same mindset. It takes time, right? We have to go through the papers, we'll look at, and as you're going through the papers, you're probably also recognizing that it wasn't in their minds about this, right? What we're talking about. And that's why this review paper is so powerful and so important. But good, keep going. I'm going to interject because as we get closer to the paper writing, I don't want to, after you present, then give you a presentation on how to write, right? That's not the goal. The goal is to interweave this so that it affects everything you do.
Mm-hmm.
Yeah.
No, that helps. Yeah. Thank
Okay.
you, Dr. Gordon.
Yeah.
So continuing with that one, the rheological properties of these nano-modified asphalt binders have been identified, and it has been found that the viscosity of asphalt binders increased due to various degrees of addition of nanomaterials. However, it has also found that with the excess amount of nanomaterials, the viscosity also decreased. And the use of nanomaterial in asphalt increased the complex modulus of asphalt while increasing the G star and decreasing the phase angle value. And eventually it has been found that the fatigue life of nanomodified asphalt binders improves. So we can see the fatigue life for the control asphalt and the nanomodified asphalt with different percentages of this nanomaterial. So we can see the values for the NF, which is the fatigue life, is increased for the nanomodified asphalt in all of them.
Mm-hmm.
And the volumetrics has been also summarized from different studies here. We can see the different nanomaterial has been used here, and the optimum binder content corresponding to the different percentages of nano content, air void, stability flow, and the VMA. It has been summarized from different studies using these nanoparticles here. So where it has been found that for some of the nanoparticles, the air voids is increasing, and also we can found that for different percentages, suppose nano titanium dioxide, nano silica, the air void is decreasing, while the VME is also decreasing. But in other cases, it has been found that suppose in gwo soil, the VMA is increased after adding these nanoparticles to the mixture. And the performance has been also summarized in this paper from different studies. So we can see the indirect tensile strength in kilopascal with the different percentages of nanomaterials, the graphene oxide, nano zinc oxide, nano calcium carbonate. These are presented here in dry condition, and these are in wet condition. So we can see that the strength is the indirect tensile strength is like increasing for the nanosilica with the same percentages where with the graphene oxide and with the nanoclay we can see it stays almost similar all out through these percentages from 3% to 9%, and almost same result is represented in also in the wet condition. We can see for the nanosilica, it has the most obvious result with the increasing values of the indirect tensile strength, and also it stays almost similar with the nanoclay in different percentages.
So in this particular slide, right, you want the yellow one, is that right?
This one is showing a better result than nanosilica with the percentages.
Yeah. So as you increase more silica, nanosilica, it increases. You get the best bang for your buck, right? You're getting a better increase versus let's say the green, right? The green one, you get an increase, but I mean, do you get it? Does it continue to increase? Can I extrapolate the line? Was it ever done, or was it like this because they only tested that range?
Yeah, they tested within this range. I mean, 1 to 3%.
Okay, so now we have to look at the slope, right? Because they only tested within the range, so we have no slope increase or barely any in many of the materials, and then in the ones with the great slope or the greatest slope is the one in red. Or the very one to the left, right? Okay, that is a huge slope increase. What is that?
It is gwo2.
Okay, so gwo2, and then, but we don't know if you extrapolated this, if it would just nobody did it at 3%, 4%. Is that correct? Or in the paper you looked at, it didn't do it, right?
Yeah, in the paper it didn't.
Right. The paper didn't do it. But then if I look at slope, right, then I would want to look at, right, did anybody do it? That paper didn't do it. Did anybody do this so that I can complete the picture, right? Right, the extrapolation at the higher percentage. Now let's go back to the slide before that, and we look at okay, so this is the volume. So Zicotherm, they did very low percentage, and then where is the volume? They didn't measure the volume increase.
No, these are the like percentages in what they use the gwo2, and these are the properties of the nanomodified asphalt mixtures.
Right. So VMA percentage, what happened to the numbers there?
Oh, yeah, they didn't identify that one because here gwo2 has been only added as a organosilane, which is the chemical to create the to increase the binding properties of the asphalt aggregate to the binders. So they didn't mention the volumetrics for these studies.
Right. So not only are they not mentioning the metrics, right? And then when you go down to the graphene oxide one, they didn't mention the metrics either. Right. So is that a flaw in the industry, or that they don't measure that metric, right? Who knows, right? But it wasn't mentioned, and all you're doing is you're reporting. These are not your experiments, but people publishing, right? And they're leaving out these categories, right? So even though the slope wasn't, like, if I just looked at slope and I said, oh, that's very impressive, right? And I want to chase this down, already we see a flaw in the volumetrics, right? And then Yeah, and then as you write this, does the air void percentage matter? You have this in the column. Apparently everybody has listed this, right? And they're all around this this increase, right? It increases, and somehow nanosilica made a decrease at the 1%. That might be an error, right? So this might be an error. We don't know if that's an error, but seemingly things increase, but that one decreased. If it's not an error, that's interesting, right? So just something, right, as you're comparing numbers, because if you now go to nanocolumnite, right, while the slope may have already screened it out, somehow it lowered the air voids, right? I don't know what that means, right?
So, Gordon, actually, so the thing is that this slide basically generally before conducting any performance testing for an asphalt mix, so what we do is that we carry out the mix design to determine the optimum binder content. So it's like how much optimum asphalt binder to be added in that mix. So most of the specifications says that the binder content should be selected corresponding to an air void content of 3 to 5%. The air voids.
Okay, so they're just saying that they were within the range.
Yeah, they are within the range, the air voids.
And then what about the NMA though? So that after it's been modified, right? That you've got your control, which is what it is. So when they actually do it, they're just saying that they're within that range, right? Is that what they're saying? Is that the column? The purpose of the column is that was within 3 to 5%, right?
Yeah, within 3 to 5%.
Okay, so then the nanocolumnite, right, is not within the range once they modified, right?
Nanocolumnite. Yeah, 3 to 5%, like 4.66 is the air void here.
Yeah, but that's the control. But once they did the modify, right?
Yes, yeah.
It fell below, right? So the more I know why these numbers are there, you see how I'm not, you guys, I've done a lot of research, all kinds of things, but the more I know why it is, right? Then suddenly, oh, I can pick and we can have a conversation, right? The more you write the paper, right, from a perspective of an urgency, right? There's nobody who doesn't understand what the word urgency means, right? So then suddenly, or climate extremes, everybody knows that. We had the warmest November. What does this mean? It might mean that we're getting more cracks or holes that are from 2024's November, but it won't show up until 2026, but they'll all show up together, right? So how you present that, right, becomes the key in hitting somebody who is from a politician to a governance, right? When they govern, they don't know anything about asphalt, right? They have to learn how to govern. But then if they don't know the urgency, right, or they don't know these things, so it's ultimately in the art of the presentation of what you present, right, that is very important, because you're showing a slide with a lot of numbers, right, a lot of numbers. And then typically what I did was I let you present, and then I don't really go into the numbers too much. But if I did go into the numbers and you gave me all these numbers, and then there was an outlier in the number, you should use that to your advantage, right? Let's say if this was a presentation that, by the way, not only are, this is the standard, but it fell out of range and it was still published, right? Right. It's still published, or it may not have been mentioned. This is important consideration to, for us to see that perhaps we can standardize our objectives a lot better with our research, right? Our research review, right? Because we didn't do the experiments, but we're reviewing all of them from a perspective that was not standardized in the academics and which affects the industry on the urgency sense, and we could actually impact all levels of research, right? So that becomes in your introduction, right? A call to action, right? Yeah. Keep going.
Okay.
All right.
Okay. Thank you, Dr. Gordon. Here the improvement in fatigue life and the rotting life has been summarized using different nanoparticles in different percentages. So where we can see, while using the nanosilica in 2%, graphene oxide at 1.5%, and gwo2 at 0.1%, and nanohydrated lime at 2%. From different studies, it has been found that the fatigue life improvement was 36.22%, and rotting life improvement was 12.1%. And the rest has been done for the rest of the nanoparticles here. So we can see the comparison between the fatigue life and rotting life improvement for different nanomaterials.
So, so again, that is another very interesting slide, right? In the sense that if we go back to the one with the zinc that was in there, right? The zinc oxide. Well, we actually can see the zinc oxide here with the X, and you don't have an improvement in the fatigue life, right? It wasn't even listed on here. The slope value isn't there. It's just way at the bottom, right? It's buried in there. But then you see that the purple one, the one with the triangles, right? The purple triangle, that one pops out, right? That one pops out more than the red dot. But then how come in the fatigue life, the graphene oxide goes to 70%? Where is it on this how come I'm not seeing that here?
Nadal, can you show where is nano titanium oxide in the graph?
No, not
Here?
the titanium.
Nano,
Graphene oxide.
graphene
It's
oxide.
the red one, right? Red circle, right? That one,
Graphene oxide.
yeah, that one only has that's buried in there. Do you have a graph that shows that the fatigue life and the rutting life improvement? Because this is fatigue life, right? So I don't see, looking at the picture, the 70% improvement that you show here. How do you see 70% improvement from the visual? Is that an error when you put the graphene oxide? Did you? Why doesn't it look like it's a higher fatigue life?
So this graph they summarized from like the paper from where they summarized. They didn't actually mention the rotting life improvement. So they provide only the graph for the fatigue life here. So this is the percentage from there, and they collected the rotting life improvement from different paper where they compared this one. They summarize these two values in here in their paper.
Okay, so same authors for fatigue life and rutting life improvement?
Yes, these were same authors.
Okay.
Yeah.
Okay. Right. So yeah, I mean you have 46 as a maybe.
I mean, yeah, this is from different paper. This is reference from 46, and this graph is from a different paper.
Okay, so these are different papers, and because if I look at the picture of fatigue life, right, and then I look at fatigue life on the column there, the written one, I don't see the number 70, right? From slope, from where it is. In fact, if I looked at it, I would say that the fatigue life of the graphene oxide, even though it doesn't say, you know, anything really very much, but just looking at, I would say that the nanosilica is better than the graphene oxide, but you can't see it from the picture, right? Is that what you're saying, that the picture is not correlated to the column of fatigue life improvement?
Yes, because these information are collected from different paper, and this information, this graph is collected from another paper.
Oh, so maybe it's maybe something happened. It's incorrect because you're only getting sub 5,000 on fatigue life in the picture, right? And then in nanosilica, you're getting 30,000 plus. If you raise the percentage to between 5 and 10%, like 8, let's say 8%, you get to 30,000. Graphene oxide would not come close, right? Right?
Mhm.
Yeah. So by the way, because my specialty is in silicon and also graphene chemistry, I'm thinking, all right, well, hot mix asphalt, right? You're gonna hot mix it, and then the oxygens on the graphene oxide will react, and you may get varying percentages of graphene, right? How you lay the oxygens on the graphene oxide as the oxygen pops off, right? And covalently bonds or leads to these things may give you grabbing strength, right? Almost like sandpaper, grabbing strength. So it also might vary. So then in my mind, I'm sharing with you, in my mind, I'm thinking any reactive chemistries, right? At those temperatures. And then the lime, I mean, you're not going to get any real benefits on the reaction, but it is interesting that you get, if we're talking about cheap material, right? Or even the ability to counter acidity from the acid rain, adding calcium carbonate, right? Lime is going to have pH neutralization effects, right? So it's interesting to see that you have a 36% improvement in that, right? Yeah. And then also if let's say the other material is very expensive and I'm just trying to boost nano content, right? Because 20% allows me to control my costs and I can go there. Wow, the ability to go up to 20% is possible. Imagine doing that with nanosilica. Can't do that, right? So or a graphene oxide can't do 20%. I mean, so that might be, from a cost perspective, nano hydrated lime maybe I don't know the pricing of this, but it might be very interesting, right? So you see how once the perspective changes, suddenly, your impact also changes. Government budgets and
Yes.
things like that. Yeah.
Dr. Gordon. Yeah, they also summarize the cost for this
good
materials at the end.
Yeah.
Imdadul, can you clearly explain what this improvement is based on the figure? What is the improvement above? That is another confusing part. Fatigue life improvement is with this modified and unmodified, right? That's 70.38. Where is the data for the unmodified? So there is something missing, right? So there's another piece of this puzzle missing.
In this graph, Dr. Mehta?
What is it improving compared to what? You see my point?
Yeah, I got your point. Yeah, but in the paper they mentioned only the nano-modified asphalt.
Just forget about this graph for a second. Your 70.38 is a fatigue life improvement is without graphene oxide compared to mix without the graphene oxide. Is that what that 70% means?
Dr. Mehta, it is like with 1.5% graphene oxide, the fatigue performance has been improved by 70% when compared to the conventional mix.
Okay, that's what I meant. So without the graphene oxide, correct?
Yeah.
Correct. And what you are seeing in the graphene oxide on the left side, you are seeing modulus, you are seeing 45 and 46. So 46 is for non-modified asphalt mix in the same row, an increase in modulus values compared to bituminous mixes, right? So that's the bracket number is a percentage.
The reference actually. No, Dr. Mehta. This bracket
in the
number
graph,
is
the numbers are literature review papers.
Yeah,
I know. That I understand. So 70.38. So what is missing here is in fact, graphene oxide is almost showing a flat fatigue life, right?
Yeah.
Right. It's not necessarily the slope, but it is literally, the fatigue. It's not the slope. It is just whatever the number is, right? Correct.
Mm-hmm.
So the fatigue life on an average is around 4,500, right? Correct.
Yes.
Right. Give or take. So what is missing is what is it for a control is missing.
Yeah, control one. Yeah, the control.
I see. So it's not the slope, but it's just that number 4,500, right? And I think Dr. Gordon is raising a very good skill that I've been saying, you own everything that is on the slide, right? And he is really making you realize it. Does that make sense? Every number you put in there, you need to be questioning it. You put it, you own it. Does that make sense? Even if it's literature review, if you can't understand it, then you have to caveat it, right? We have to still look at this. This is missing because at this point, I don't understand this information. I'm just presenting it. Does that make sense? So this is a very great skill set that you are learning. So going forward, you cannot blow it up. Oh, this is literature review. I cannot complete the story. You got to at least explain it that I will make an effort to complete that story. Does that make sense? Otherwise, everything has to make logical sense. Good?
Understood.
Thank you.
Yeah, we can look for different papers to fill that
Right.
gap.
Yeah, but in general, also when I look at the other slides and the other tables, right, the way he explained, right? So just every table there is a story, right? And that's what you need to be able to capture. So good stuff. Thanks.
Thank you, Dr. Mehta. So here is the cost analysis that they presented, summarized from different studies. We can see the nanosilica, nanoclay, and different nano materials and their cost per kg for these nanomaterials only. And while preparing the mixing for unmodified one and the nanomodified binder, the cost for this. So with the different amounts, we can see the cost for graphene oxide turns to be the most expensive one as a nanomaterial per kg, while the gwo soil is the cheapest in terms of the nanomaterial price, while considering the preparing the modified and unmodified mixtures, the nanosilica represents the cheapest price among all of these nanomodified asphalt binders. And some of the challenges that has been found while considering these nanomodified asphalt binders and mixtures, one of them is the environmental factors, because there could be leaching, groundwater contamination, and possible spreading of nanoparticles in the open air while mixing. And also there is the incompatibility and phase separation with this nanomaterial, and also for handling the skilled laborers and workers are needed, and some sophisticated equipment is also needed to for the proper mixing of these nanomaterials into the binders. And the major challenges has found that at present there is no standard guideline for the application of nanomaterials in asphalt mixtures, and different nanomaterials have their own properties, so they need different mixing techniques for the homogeneous dispersion. And also the application of nano asphalt on large scales can create some environmental concerns which has to be controlled, and the life cycle cost analysis for all of these nanomaterials has to be performed. And one of the major issues while mixing these nanomaterials has been found is the storage stability. So in this paper, it has been summarized the storage stability they found from different studies, that it shows that the nanoclay decreases the storage stability of asphalt at lower nano content. However, it increases while it has the higher nano content. And the storage stability of nanomodified asphalt decreases at a certain increase in nano material content. So it has been found from different studies that while obtaining at 5% of nano content, it shows the better storage stability. And the nano alumina helps in improving the storage stability at high temperature with the styrene butadiene styrene modified asphalt. However, when the storage hour is more than 48 hours, then it can impact the storage stability, and it reduces the value for storage stability. And carbon nanotube, graphene oxide, nanoclay, and nano alumina shows the better there was less difference at the top and bottom softening point, and it was less than 2.5 degrees Celsius. So to solve the storage stability, another study has been presented where they use the nano alumina and crumb rubber and SBS polymer modified binder to study the storage stability issue here. And they are blending in high shear and blending in high shear for 60 minutes in 3000 RPM. And scanning electron microscopy has been used, and also the softening point difference has been used to identify the storage stability on top and bottom layer. So the results they got here in their study, we can see from this figure, after adding different percentages of nano-alumina content while starting from 0 to 3%, the softening point difference between the top and bottom layer reduces for the, this is with the control, this is AC20 is the control one, and this is with the SBS polymer modified, and this is with the nano alumina polymer modified binder, and this is with the crumb rubber modified asphalt. So we can see the nano alumina, it reduces with the increasing percentage of nano alumina, that softening point difference is reducing. However, it's not within the range. It has to be lower than 2.5 degrees Celsius. But with the crumb rubber, the difference is also reduces. So here they found that the reduction in viscosity actually, the increasing in viscosity is reducing the settling velocity for these particles. So that's why the composite with the 3% nano alumina and polymer modified exhibited the 70% reduction in softening point difference, which shows the better storage stability. From this point, Swati will continue for the rest of the presentation.
Good morning, everyone. So in this presentation, I'll be talking about the environmental impact of nano-modified hot mix asphalt. The reason for the study is to evaluate the efficiency of the nanomaterials incorporated in the hot mix asphalt, to determine their efficiency in absorbing the air pollutants when they are incorporated in the hot mix asphalt. So in this study, they have considered nano titanium oxide in a crystal format, and nano silica and asphalt concrete of grade 10. The nano titanium is selected because of its properties, like it is a very good air purifier, and it has low cast, and it reacts very fastly. And nano silica is considered because it is effectively used. It is widely used in the hot mix asphalts. So in the study, they have considered the combination of these two materials. Based on the literature review, it was observed like from the when we consider different energy consumption industries. So transportation sector has high contribution to the environmental pollution. We can see from the data, like the amount of emissions from the generated from the transportation infrastructure. So in like there is a lot of carbon CO emissions 96.9, and CO2 emissions 24.9, and other oxides of nitrous oxide 49.6, which are considered to be the major concerns of air pollution. And these are the following tests conducted to evaluate the properties of the materials and the performance of the mixes. So NOx analyzer and the photoreactor, this test is used to determine the amount of nitrous oxides of nitrogen absorbed by the hot mix asphalt incorporated with the nanomaterials. Next slide. So these are the chemical compositions of the nano silica and nano titanium oxide. If we see the physical properties of these nanomaterials, nano silica exhibited a high surface area, surface volume ratio. So this property is helpful in improving the absorption rate of air pollutants from the atmosphere. So in this test, like they have considered 4 different types of the mixes, considering different proportions of titanium oxide and silica. So the method of blending of these nanomaterials with the asphalt has been mentioned in the literature review. First initially the silica oxide is blended with is mixed with the titanium oxide in the form of a silica gel, and then the composite of this nanomaterial is added to the asphalt using high shear method. So then the modified asphalt binder is tested under scanning electron microscopy to understand the real morphological properties of the binder, and then they were subject to the rheological properties like the penetration. Other binder tests were carried out. So from the binder test, it was observed that there have been an increase in the properties of the modified asphalt with the increase in the proportions of this nanomaterial. So type D has provided better binder properties when compared to conventional asphalt. So then the mixtures have been produced, and the type A, type B, type C, type D asphalt mixtures have been produced, and initially in order to evaluate that air pollutants from the vehicle, they have prepared a sample of this size, and then they have subjected to the sample to the UV light, the one which is connected to the exhauster, and also subjected to the vehicular emissions. So from this test, they have observed initially they have conducted only the test on the modified mix. So it was observed that nano titanium oxide and the silica were not able to absorb more air pollutants. Then what they have conducted is they have spread a layer of titanium oxide over the asphalt mixture, and then it was observed that this layer of titanium oxide was able to absorb more air pollutants from the atmosphere. Next slide. So based on the performance, based on the test results, it was observed that these nanomodified have decreased the growth rate of the micro cracks and the cracks developed due to creep. This was determined by carrying out the direct shear rheometer test, and they have carried out the fatigue performance test also, and from this graph it was observed that the fatigue performance improved with the for the nanomodified asphalt mixture. And also it was observed like when compared to the conventional mix, in the nanomodified mix has absorbed NOx, and also with the increase in the nanomaterial content, there has been an more absorption of nitrous oxides. And so after the layer of the nano titanium oxide showed about a 41 to 63% of reduction of the nitrous oxide pollutants when compared to the nano modified mix. This what I have earlier explained. So yeah, so from this graph it is observed like when compared to the conventional mix, with increase in the time, the rate of absorption of the nitrous oxide has been increased for the nano-modified samples. The next slide. Yeah. So this is another case study where the life cycle assessment of nano-silica modified asphalt mixture has been evaluated during the production phase. This doesn't consider the whole life cycle. So only the during the production phase, the life cycle analysis is carried out. In this study, they have considered these what are the materials that have been used in the production of the nano materials and asphalt materials, and how much energy is required for the 1 kg unit production of this nano silica. So the right side image explains the considers the production stage of the asphalt where nano materials are produced and then transported to the milling terminal where binder extracted binder is also added to this modified added to this nano materials, and these modified asphalt materials will be added to the aggregates, crushed aggregates, and then fine aggregates, and the final nano modified asphalt mixture will be produced. Next slide. So in this life cycle assessment, they have used a software, open software life cycle impact assessment, and what was observed is that when compared to the conventional mixes, these nano modified asphalt mix showed 0.4% increase in global warming, 0.8% increase in respiratory effects, and 0.009% increase in ozone depletion, and 0.98% increase in eutrophication, 1% increase in the human health, 0.7% in photochemical oxidation, 0.96% increase in human health, non-carcinogenic agents, 0.72% increase in ecotoxicity, and 0.85% increase in acidification. So, based on this, the impact of nano silica on global warming is about 0.4%, which is comparative, which is more or less equal to the conventional asphalt mix. But if we see, there is a greater impact on the human health, which is carcinogenic and also non-carcinogenic. So this can be a major concern of incorporation of nano materials in asphalt mixtures. And the higher rate of acidification, it is maybe due to the presence of sulfuric acid used in the production of the nano silica, and that causes excess production of the sulfur dioxide and nitrogen oxides released into the atmosphere, and also during the transportation of the materials. So increase of this H+ ions may lead to acid rains. That can be another disadvantage of this. Next slide. So another method is they have carried out a normalized score method. So in this method, it was observed that this normalized score, it basically a log scale in which is segregated into two different zones. The one, if you can see in the graph, there is a horizontal line which is at 1. So the zone above that one is considered as zone B, and below it is considered as zone A. So in it is observed more is the normalized score, more is the adverse effect of that material. So the one which is falling in the zone A are performing better when compared to the one which is falling in the zone B. So from this, it is observed that nano-modified asphalt materials are performing better in global warming. We can see from this in terms of global warming, ozone depletion, and photochemical oxidation, eutrophication, ecotoxicity, they are performing better when compared to the respiratory effects and carcinogenics, and human health non-carcinogenics, and acidification. Next slide. So from the overall findings, it was observed that nano silica is like it does because of the less proportion of the less change in the global warming, it can be concluded that it will not, nanosilica doesn't have any unreasonable risk to the environment, nor it will affect the life cycle environmental profile of the asphalt mixture. But in the futures, like the full scale life cycle analysis of the nano modified asphalt mixtures to be carried out, and for different materials to be carried out, because like nano silica properties and the other nanomaterials will be different, so we cannot conclude the results of the nano silica with the other nanomaterials to confirm the sustainability. Next slide. So this is our future scope of work, and these are the references.
Those are very low citation numbers, right?
Yeah.
Those are all, nothing was in the triple digits. So you can see what I'm saying to you, right? Is that if you want to create something that people will have impact, it cannot be just siloing one of these things. And if we can accomplish, of course, the high citation result, and then lead to long-term impact with consideration of, okay, cost, consideration of, but right now, before we get there, is let me get your attention with this group that has helped us impact all the writings and all the papers, right? One of the things that you could go on and on with this is that if it's helpful for all these NOx and SOxes, these oxide gases, but what if I have large volumes of these things, right? What happens, right? And then can I mix some graphene oxide in there along with some of the nanosilicon, right? So that I now have a combination, right? Nanosilica, a combination of this, so that I get some properties of effects as well as the other, right? As well as these other properties. So can I do that, right? But again, saturation is a question I have, right? Is that does it, once it's saturated, how does it get released, right? Is it catalytically breaking this down? But even if it's a catalyst, it will run into a enzyme substrate model, right? Where if it saturates, then you still need to wait, or you have to add more. What exactly, right, is this is the limits of this? And then the nanosilica did not have certain benefits in the earlier part of the presentation, right? What we're looking at on the rutting and these other things. So maybe the answer, right, will be in the unconventional, right? The conventional is what we know, but the unconventional approach is you don't just find, if we're trying to make the best naan bread, right? We might not be just looking at the wheat only, right? Maybe it's the grinding, maybe it's maybe it's the oil, right? And then it's everything combined together. And then of course it's the cost, because if it's the best thing, then nobody cares. And what makes graphene oxide very interesting is the numbers of oxygens on there affects your cost, where the oxygen is positioned, right? If it's a ketone, it'll be different than a carboxylic acid, than an aldehyde, right? These are all extremely different. To call just oxide, right, would we be overlooking, right? And then where are we putting this, right? If we're trying to repair some things versus if we're trying to lay a road down, that's different. Road down, we want to mix it all, as you identified, whether it's on the surface or embedded inside, it affects its ability to purify. And then that's when I asked the question, if the location of exit, then how about the amount of exposure, right? Can it be clogged, right? Remember when they had all these wonderful things that allow the impervious materials now is pervious. But if the pervious becomes clogged, then then what did we? It gets clogged over time with other materials. Then are we just lying to ourselves, or this is a temporary solution, right? And then we didn't do the ability to spread the heat. Which materials spread the heat? So let's say we found all of these things, right? And then could we combine them together? Maybe nobody's ever done that. And then in your paper, as you're writing, you write, not only do we need more experimentations, right? More people to jump on this, but also, what about mixing them together? What happens then, right? So that's for paper writing, right? Is that you haven't done this. You know, the best essays are not the ones that you talk about what you've done, right? But you actually write what you will do. But they say you don't have any experience doing this. Well, you know, but you will do this. There are people who have a lot of experience who won't do anything, right, about the problem. So it's not about the past only, right? The past is important, but to how you write about the future, right? Think about the presidential elections. Both candidates talked about what they will do in the future, right? But both of them have been in public office. So what did you do about the president in the past? So, right, it becomes really interesting as we vote for based on the future. And what we're trying to say is that in the future, there's a serious problem. And the bet was made, right? The bet was made because I have a certain skill set. And they said, oh, if he jumps into this laboratory, maybe there'll be a transformation. There'll be transformation to a problem. And then, of course, you're interfacing with me and you're working with me. If I'm not really able to see differently, right? Then this was all made up. But if I am able to change how you think, how you present, how you write, and then you do get a citation in the triple digits, right? Then and it goes on and on. It's not just 1 year. It's next year, 2028, they'll still be talking about your paper, right? Our paper, right? Then that's also meaningful. Is the long tail citation, not just the instant, right? You know, and then it becomes something that's referenced by all people writing about this, because these people changed the future, changed our future from a review that made us, helped to make us think, right? And I'll give you one last one, is they didn't say this is a movie about sharks eating humans. The movie was just titled Jaws. It could be any Jaws, right? But it was just Jaws, and people would watch it, right? So it is in the art form of how to position the science from a level of urgency that if do you want more potholes? Do you want more calamity? Do you want to have municipal budget issues, right? Across various spots across our nation, right? Across our states, presenting it that way gets them to read it, and then inside of the content, you must optimize the content to create an effect. Almost like if you were playing a song on the piano, then you have to play it with a way that moves people. But if all your fingers are just as stiff, even the ones not touching the key, I'm not a piano player, but I'm just saying, right, when we think about this, right? But if you're also then able to sing, and the pump of the piano just helps you, you're not the best piano player, but you sing, and then but the combination makes you very unique. You'll get, right, you'll get attention, right? Versus, all right, you play the piano and it doesn't sound very good, so people just talk over you, right? It is, oh, ho hum, it happens, right? It's essentially the same when you write a paper, when you give a talk. I mean, it is from what perspective that you share the information and you get them to continue to think, and to be able to, after reading this paper, I will do so much better because of you, right? And that's the role each of you serve in us putting together this write-up, right? That will go on for, maybe impact them for 10, 20, 30 years. But we're over time. So we try to compress all this in 1 hour. Please continue to do what you're doing, right? And I hope you you use the chat and you use the changes in the titles. Just don't just use the title, but think of the titles I put in there. So it just gives you the perspective to write, right, from that, and also search for the journals from that, right? And then yeah, and we call nano just nano, but sometimes they're fibrous, other times they're like spherical nano. The structure actually matters. Like if we're making something called origami, right? We're folding this paper to make it no longer one sheet. Well, the structure of the nano also matters. So the structure activity relationship, if we were talking about drugs, right, and pharmaceuticals, then that affects the overall compound. So this is just, that's a lot. I want you to just spend the time thinking, and we'll meet again in 2 to 3 weeks.
Do we have a Google Drive or something, guys, where everything is stored?
Yeah,
I think you should.
yeah, we
Yes,
have a Google
yes,
Drive.
Dr. Mehta.
Yeah, we have it, right? And shared with Dr. Gordon, right?
Yeah.
Okay,
Great.
great. Awesome. Sounds
All
good.
right.
Thank you.
Thank you.
Thank you, Dr. Gordon, for your time. Thank you,
You're
Dr.
welcome. Thank you for yours. Time.
Thank
Oh,
you,
by the
Dr.
way,
Jain.
time is our most valuable asset, right? People say that. That's actually not true, right? People say they want to kill time. So why would it be your most valuable asset? They play with their time. I believe, and this is just my perspective, is your awareness changes your value of your time, right? So the more you're aware of what you're doing, you might need very little time, right, to become. So raising your awareness is your most important asset as a future, right, professor, future, I think, is if you can raise your awareness, right, and practice. How do you raise your awareness? To practice like these group sessions, right? I hope I'm raising and changing your awareness so that you will look at this and write it differently. And it is in that awareness that you become extremely efficient with your time. You actually do certain things that lead to impact. All right, great.
Yeah.
I will see you in 2 to 3 weeks. I know the holidays are coming up, so we'll if I looked at it in 2 weeks, I think that would be December 6th. We should be able to do it then. But I will look and then I'll message everyone.
Yeah, thank you so much. Thank you, Dr. Gordon.
Thank
You're
you.
welcome. All right. I enjoy having you guys. This is
Thank
great.
you, Dr. Gordon.
Young.
Thank you,
Thank you.
Dr.
All right. Bye-bye.
Thank you.
Bye.